Okay, welcome back to the deep dive.
Hey there.
So today we're tackling some really fascinating source material.
Absolutely. It's a collection of research papers, basically, from a book called New Carbon-Based Materials for Electrochemical Energy.
Right, and this book compiles work from a NATO Advanced Research Workshop.
Yeah, part of their Science for Peace thing. It's volume 229 in their Chem Physics series. Barsakov, Johnson, Donninger are the editors listed.
Okay, so quite a specific source.
Definitely. And our plan really is to try and unpack it almost, chapter by chapter.
Digging into the details.
Exactly. We want to pull out the key takeaways on how these carbon materials are actually being, developed and used for storing energy electrochemically.
Which makes sense because carbon is just fundamental here, isn't it?
Totally. It's everywhere. Batteries, supercaps, fuel cells.
Abundant, pretty green.
And it's the conductor. It's making those pathways for the electrons to move.
Yeah.
But, and this is a big but in the source material, even though we use it all the time, fully getting a handle on its role, how stable it is, making it work really efficiently, that's still a big challenge. Lots of active research.
Okay, sounds like we've got plenty to dig into then. So let's start right there with carbon's basic role. It's more than just structure, right?
Oh, absolutely. It's not just holding things together. Sometimes it's the active material doing the charge storing itself, like you see in some battery chemistries.
Okay.
But maybe even more universally, it's that conductive network. It's like the wiring, distributing the charge, making sure electrons can get in and out easily.
So even if another material, say lithium ions, are doing the storing, the carbon helps it happen.
Precisely. It provides the electronic pathways. Without a good carbon network, you can't access the stored energy quickly or efficiently, especially when you need high power.
Right, the speed matters.
It really does. And making that network effective and crucially stable within the battery's environment, that's a theme we'll see again and again in this research.
Okay, let's start breaking down the specific applications then, treating these like different, chapters from the book. First up, supercapacitors.
Right, supercaps. And a big chunk of the research discussed here focuses on activated carbons.
Activated carbons.
Yeah, carbons that have been treated, often chemically, to create a really high surface area with lots of pores. Specifically, they talk a lot about using potassium hydroxide, KOH activation.
And they made these from different starting materials.
All sorts. Coal,
Yeah.
different types of semi-coke derived from coal or pitch, even just raw pitch. The aim was always to create these super porous carbons for the supercapacitor electrodes.
So when they're studying these KOH-activated carbons, what exactly are they looking for? What makes one better than another?
A whole suite of properties. Obviously, capacitance is how much charge can it hold, but also the pore size distribution.
Are the pores big enough for ions to get in? Too big.
Then there's how well it interacts with the electrolyte, its wettability, or its hydrophilic character, and even things like the conductivity of the carbon particles themselves and their size.
Why do all those details matter so much?
Because they all directly impact how that electrochemical double layer forms.
The double layer. Can you give us the quick version of that again?
Sure. So picture the electrolyte ions lining up right at the surface of the carbon pore. That's one layer of charge. And then an equal opposite charge builds up just inside the carbon material itself. That separation of charge right at the interface is the double layer. That's where the energy is stored in the standard supercapacitor.
Like tiny little capacitors all over the surface.
Exactly. So you want tons of surface area, and you need the electrolyte ions to be able to get to that surface easily and quickly. Maximize the accessible surface.
Got it. Any specific findings jump out from this KOH work?
Well, they found that the starting material really influenced the final pore structure. And using things like mesophase or semi-coke, which are sort of lower temperature carbon precursors, allowed them to hit really impressive surface areas.
How high are we talking?
Like 2,700 up to maybe 3,200 square meters per gram. It's kind of mind-boggling, like packing a huge area into a tiny bit of powder.
Wow. That definitely explains the potential for high capacitance. I think there was something about carbon composites too. And nitrogen.
Yeah, that was interesting. They found certain CC composites showed a really noticeable boost in capacitance. The researchers suspected it might be linked to nitrogen atoms getting incorporated into the carbon structure somehow.
Creating extra active sites, maybe.
Potentially. Or maybe improving how well the electrolyte wets the surface. Still being investigated, it sounds like.
And how do they actually measure all this? What tests do they run?
The usual electrochemical toolkit. Voltammetry, look at current versus voltage. Galvanostatic cycling, charging and discharging at constant current to measure capacity fade, and impedance spectroscopy.
Impedance tells you about resistance and how fast things are moving.
Exactly. It helps break down the different resistance components and understand the kinetics of charge transfer.
Okay. Now, the source also talked about adding conductive materials to the electrode, not just the main activated carbon itself, comparing different additives.
Right, because even activated carbon might need a boost, or the additive helps bind everything together. They compared standard stuff like acetylene black with different graphite powders, and interestingly, even nickel powder.
And did they find big differences?
Oh yeah, especially in terms of stability. Graphite powders tended to hold up much better over lots of charge-discharge cycles compared to the nickel powder or some types of colloidal graphite they tested.
So the additive choice affects how long the supercap lasts.
Significantly. They saw things like the internal resistance shooting up after only hundreds of cycles with some additives. The thinking was that degradation, maybe oxidation of the additive or swelling, increases the contact resistance between particles over time. Kills the performance.
Fascinating. Okay, let's shift slightly. Still in supercaps, but looking at manganese oxide MnO2. Not carbon, but uses carbon, right?
Exactly. They discussed using amorphous, hydrated manganese oxide prepared by chemical co-precipitation. And the key finding here was about the carbon additive used with it.
What did they find?
Adding carbon nanotubes, specifically multi-walled CNTs, gave a significant performance improvement compared to just using regular carbon black.
Why would CNTs be better? Just more conductive?
That's likely part of it, but also their shape. Think long tubes versus little balls. The CNTs can probably form a more effective, interconnected, conductive network throughout the MnO2 material.
But the manganese oxide itself wasn't perfect.
No, it had its own issues. They noted limitations, especially when used in a full two-electrode capacitor because of some irreversible side reactions involving the manganese, depending on the electrolyte.
Okay. What about other materials? Polyaniline, PPY.
Yeah, polyaniline. It's a conductive polymer. It stores charge a bit differently than activated carbon, uses fast surface chemical reactions, what they call pseudo-capacitants.
More capacity potential.
Potentially, yes. But the catch they found was stability. It cycled well if you kept the voltage low, like 0.4 volts, but push it higher to, say, 0.8 volts, and the capacity dropped off significantly. The operating window was critical.
And did they try combining these, like PPY and MnO2?
They did. They looked at asymmetric supercapacitors. So one electrode using PPI, maybe mixed with CNTs for conductivity, and the other using MnO2.
Taking the best of both worlds.
That's the idea. Leverage the potential high capacity and low cost of MnO2, maybe pair it with the PP-CNT combo.
The source also briefly mentioned theoretical modeling.
Just a nod to the fact that it wasn't all benchwork. People were modeling how ions move through these complex porous structures, developing equivalent circuit models to understand resistance and charge transfer, even calculating things like the ideal electrode thickness for power delivery.
Okay, good overview of the supercapacitor chapter. Let's move to the next big area. Fuel cells and metal air batteries. Carbon's role here.
Still crucial, often as a support for catalysts, or as a key part of the gas diffusion electrode, especially in metal air.
Metal air batteries. What's the main draw there?
High theoretical energy density, potentially low cost, stable voltage. The big thing is they use oxygen directly from the air.
So you don't need to carry the oxidizer inside the battery.
Exactly. The air electrode, the gas diffusion electrode, is where the oxygen reacts. And carbon materials are key components of that electrode.
What kind of carbon work did they discuss?
Well, they looked at panagraphite composites, again, this time as catalysts for the oxygen reduction reaction. And a specific material highlighted was thermally exfoliated graphite TEG.
TEG. That sounds familiar from earlier. What makes it good here?
It's that unique structure, low density, like fluffy graphite worms. It gives you decent conductivity, it's pretty stable, lightweight, and crucially for an air electrode, it tends to be hydrophobic.
Repels water. Why is that important?
Because water is often a product of the oxygen reduction reaction. You need to manage that water, let oxygen gas get in, and prevent the electrode from flooding. TEG's nature helps with that balance. It supports the catalyst and provides pathways for gas and electrons.
Did they test these in actual devices?
Yep, they built small Xeon battery mock-ups using these Panateg electrodes, showed decent capacity retention, and they reported specific energy numbers around 140 Wei-Caslas for zinc air, maybe 200 for magnesium air, using Pana catalysts. And they noted the flat discharge curves, which is a nice feature.
Were there other catalysts besides Pana?
Oh yeah. Active carbon promoted with NiCO oxides, things like cobalt TMPP, which is a macrocyclic complex. There was also work mentioned on trying to graft metal complexes directly onto the carbon surface to act as catalysts.
Grafting, like chemically attaching them.
Exactly. Interestingly, that grafting approach didn't seem to work well later when they talked about it for lithium-ion battery anodes, but here it was being explored for catalysis. Shows how context matters.
They even looked at how gas actually moves through the electrodes.
Right, the physics of it. The difference between viscous flow through larger pores and Knudsen diffusion in the tiny ones. Understanding that helps you design the pore structure to get oxygen to the catalyst efficiently, especially when you're drawing a lot of current. They even pinpointed optimal metal loadings in some catalysts, like maybe 5% silver plus 7% nickel worked best in one system.
Any practical tips mentioned for making Zenair work?
A few things came up. Using really pure zinc helps. Adding inhibitors like lead or certain amines can reduce corrosion. And a simple one. Keep the air holes sealed until used to stop the electrolyte reacting with CO2 from the air. Humidity and temperature also play a big role, as you'd expect.
Okay, clear picture there. Now let's shift to what seems like a major focus of this collection, carbon in lithium-ion battery anodes.
Yeah, this is where a lot of the detailed work seems to be concentrated in these excerpts. And it makes sense. The anode is critical. The source traces the history a bit, moving away from pure lithium metal anodes.
Because of safety issues, dendrites and stuff.
Exactly. To using carbon materials, primarily graphite, where lithium ions can kind of tuck themselves in safely. Inocculation is the term.
So walk us through how that graphite anode works again.
Okay, during charging, lithium ions travel from the cathode through the electrolyte, and they slide in between the graphene layers of the graphite structure.
Intercalation.
Right, but crucially, on the very first charge, some electrolyte reacts right at the graphite surface. This forms a thin film called the solid electrolyte interface, or SEI.
The SEI layer, heard of it. Why is it so vital?
It's everything for longevity and safety. A good SEI lets lithium ions pass through, but blocks the larger solvent molecules from the electrolyte. If it works well, it stops further electrolyte decomposition.
And if it doesn't work well?
You get continuous side reactions, consuming lithium, consuming electrolyte, building up resistance, degrading the battery, and potentially causing safety problems. Getting that SEI right and stable is paramount.
The source mentions different types of graphite, natural versus artificial.
Yep. Natural graphite is mined and purified. Artificial is synthesized, often at really high temperatures, like over 2,500 Celsius, to get that perfect graphite structure. They talk about characterizing them by things like tap density, how well the powder packs, and particle size.
And the key performance metrics for an anode.
Reversible capacity is the big one. How much lithium can it store and release cycle after cycle? For graphite, the theoretical max is 372 millikiag.
Okay.
But the other huge factor, highlighted over and over, is that initial irreversible capacity loss.
The capacity you lose in cycle 1 and never get back?
Precisely. That's the lithium used up forming the SEI and maybe other initial side reactions. Minimizing that loss is a massive focus because it directly impacts the battery's usable energy from day one.
They also mention hard carbons, different from graphite.
Yes, hard carbons have a more disordered structure. They can sometimes store more lithium than graphite, interestingly, and they play nicer with certain electrolytes, like propylene carbonate, PC.
Ah, PC. I remember you saying that's tricky for graphite.
It is. Hard carbons are more tolerant. But the trade-off is often that hard carbons have even higher initial irreversible capacity loss, and the lithium ions might move in and out more slowly, poorer kinetics.
So let's talk about that PC problem with graphite. What exactly happens?
PC is propylene carbonate. It's a common electrolyte solvent, good properties, relatively cheap. But with graphite, it has this nasty habit of getting dragged into the graphite layers along with the lithium ions. Co-intercalation.
And that's bad because
the PC molecules are much bigger than lithium ions. When they force their way between the graphene sheets, they pry the layers apart. It's called exfoliation. It physically destroys the graphite structure and leads to rapid failure.
Okay, so how does the research here suggest dealing with the PC problem?
Two main strategies emerge. First, electrolyte additives.
Adding small amounts of something else to the liquid.
Exactly. Things like CO2, nitrous oxide, sulfide ions, vinylene carbonate, or some fluorinated compounds. The idea is these additives react first on the graphite surface, forming a better, more protective SEI layer that stops the PC from getting in later.
Like a sacrificial layer.
Sort of, yeah. Or just one that forms a more effective barrier. They even use techniques like mass spectrometry to watch the gases produced during these reactions, confirming, for example, that Propene gas comes off when PC decomposes,
What's the second strategy?
modifying the graphite surface itself,
Okay.
coating the particle.
Coating them with what?
Usually the thin layer of amorphous carbon, or sometimes even metals like copper or nickel, as we'll see later. The goal is to create a physical barrier or change the surface chemistry to prevent that PC co-intercalation.
Okay, that makes sense. Now what about the really high-capacity anode materials like silicon or tin?
Ah, yes, the next generation candidates.
Yeah.
They can store way more lithium than carbon. Silicon's theoretical capacity is huge, over 10 times graphite's.
So why aren't they everywhere?
The volume change, it's massive. When silicon alloys with lithium, it swells up by like 300% or more.
Whoa.
Yeah, and then it shrinks back down when you discharge. This repeated expansion and contraction pulverizes the material. It cracks, loses electrical contact with itself and the current collector, and the capacity just fades away really quickly. Tin has similar issues.
Okay, that's a serious problem. How are they trying to solve that?
The main approaches discussed in this source involve nanostructuring, making the silicon or tin particles really, really tiny.
Does that help?
It can. Smaller particles might tolerate the strain better. Or creating composites, embedding these silicon or tin nanoparticles within a more stable matrix, like graphite, or coating them with a layer of carbon, or designing complex core shell structures.
Containing the beast, basically.
Kind of, yeah. Giving it room to breathe without falling apart or holding it together mechanically and electrically.
Let's get into some specific research findings from the anode sections. The editors highlighted testing in full cells.
Yes. They made a point of saying that evaluating materials in full cells pairing the anode with a real cathode is better practice than just testing against lithium metal in a half cell.
Why is that?
It gives a much more realistic picture of performance. The interactions between the anode, cathode, and electrolyte are all happening together, just like in a real battery. Half cells can sometimes be misleading.
Okay. Now, that initial irreversible capacity loss, was there consensus in the source on what causes it?
It seems like there was active debate. They considered several possibilities. Oxygen groups on the carbon surface, maybe certain pore sizes trapping lithium irreversibly, or electrolyte breaking down on specific active sites on the carbon surface during that first charge.
Which one seemed most likely?
The electrolyte decomposition on active sites seemed to be a leading theory highlighted in the discussion. They even mentioned trying heat treatments to try and passivate or remove these surface sites, though results varied.
Any standout graphite materials mentioned?
They discussed purified natural graphite, giving an example like LBG 1025, which showed pretty good performance, only about 8% irreversible loss, which is decent, and good rate capability, meaning it handled faster charging well.
So good baseline performance.
Right. And they pointed to the SLC family from Superior Graphite as a commercial example of further improvements, focusing on controlling surface area and particle shape for better performance and safety.
And then there was that silicon graphite mix that seemed really interesting.
Ah, yes, the Psi-coated graphite. This was LBG-25 graphite with just 3% silicon added, but it achieved a capacity of 412 millag.
Which is higher than graphite's theoretical max of 372.
Exactly. That's over 110% utilization compared to graphite alone. It suggests the silicon isn't just adding its own bit of capacity, but somehow enabling the graphite to perform better too. Or maybe there's a synergistic effect in how the SEI forms. Really intriguing result.
So blending materials is a theme.
Definitely. Combining soft and hard carbons was proposed, and the editors noted that commercial approaches often involved coating graphitic carbons with thin layers of other carbon types. They also showed good results for a blend using that thermally exfoliated graphite, TEG.
The source also got really fundamental, looking at the actual steps of lithium going into graphite.
Yeah, detailed studies looking at the staining process, how lithium fills the layers. They found some weird things, anomalies in how the dimensions changed, or the speed of the reaction, or even the thermodynamics, especially during certain stage transitions.
What caused those?
They speculated it could be due to disorder in the graphite, internal stresses, the influence of the SEI layer, or maybe even temporary intermediate structures forming. It shows just how complex that intercalation process really is.
Some Russian carbons were also mentioned.
Briefly, yes. Grades like SPG and SNG were tested showing good capacity, around 340 milliag, and decent cycle life, though maybe slightly higher initial irreversible losses, like 20%.
And back to surface modification for PC, they specifically looked at this for high-power uses.
Right, for things like hybrid vehicles where you need good performance with potentially PC-containing electrolytes. They showed that surface-treated graphite, like an SLC grade, performed much better in PC blends than untreated graphite. pretty clear evidence that the surface treatment was blocking that harmful PC co-intercalation.
And they even tried coating graphite with actual metals, copper and nickel.
Using a technique called fluidized bed chemical vapor deposition,
Yes.
FBCVD, they put copper or nickel nanoparticles on the graphite. The copper coating came out looking best. Better cycling, lower irreversible capacity compared to nickel or the plain graphite. The idea was the copper nanocytes maybe improved particle-to-particle electrical contact and help block the PC.
Lastly, for anodes, tin oxide.
Yep, SNO2. Another high-capacity option via reaction and alloying with lithium. Again, volume expansion is the big hurdle. The source showed results for thin films and also for composites, mixing tin oxide or silicon nanoparticles into graphite, often using TEG as a porous host structure to try and manage the expansion and keep everything connected.
Wow. Okay, that anode section was dense. Really shows the challenges.
And the creativity in trying to solve them.
Let's quickly cover some other carbon types mentioned before we get to cathodes. Carbon aerogels.
Mentioned mainly for supercapacitors, again, due to their high surface area. There was a curious side note about them potentially storing a small amount of hydrogen gas, maybe around 1%.
And carbon nanoscrolls, what are those?
Kind of like rolled up sheets of graphene. They discussed making these and carbon composites in a simpler one-step process, starting from graphite intercalation compounds, or GICs. They noted some unusual open-ended structures.
GICs, compounds where things are already inserted between graphite layers.
Exactly. And they also looked at how to make those GICs themselves more stable. For instance, stabilizing graphite nitrate by co-inserting things like acetic acid and water, maybe through hydrogen bonding.
And testing graphite stability.
They developed an electrochemical test, basically cycling the voltage up high repeatedly to see how well different graphites resist oxidation. Found that TEG, modified with boron oxide, B2O3, was significantly more stable than regular TEG or natural graphite.
Last one, carbide-derived carbons, CDCs.
Made by reacting metal carbides with chlorine gas. The key thing is the synthesis temperature controls the structure. You can get anything from amorphous carbon to quite graphitic carbon, depending on how hot you run the reaction. More tuning possibilities.
Okay. Now, even though the book focuses on carbon materials, it did touch on cathodes, often because carbon is used in them as an additive, right?
All right, or the analysis techniques were relevant. So a few cathode-related sections popped up.
Like power fade in cathodes.
Yeah, this was interesting. Looking at high-power cells with a nickel-rich NMC-type cathode, Len is 0.8, 0.15, all ill 00502, they found the main reason the power faded over time seemed to be degradation at the cathode.
Not the anode.
Primarily cathode in this case. And they used some cool microscopy techniques like AFM, that can sense current, and Raman spectroscopy to look really closely at the cathode surface. They saw evidence that the carbon conductive additive was actually moving around or pulling away from the cathode particles during aging.
Losing contact.
Exactly. Which would increase resistance and reduce power capability. Shows the carbon additive's role is critical there too.
Manganese oxide came up again, but as a cathode.
Yes. Amorphous MnO2 NH2O, the same stuff as in supercaps, was looked at as a potential cathode material for lithium batteries. Preliminary results showed it could reversibly intercalate lithium, but the capacity mentioned seemed a bit low compared to standard cathodes like LMO. They also discussed general properties of manganese oxide's defects, conductivity, the role of water, and briefly mentioned trying to electrodeposit films of other metal oxides like nickel or cobalt.
There was also a review of synthesis methods for oxides.
Focused on the Puccini method. It's a wet chemical way to make complex mixed metal oxides, like the ones used in many modern cathodes. You use acids like citric acid to chelate the metal ions, form a polymer resin, then burn it off to get a very fine, uniform powder.
Aiming for a really good mix of the metals.
Precisely. Uniform cation distribution at the atomic level, which is key for good electrochemical performance. The source did mention some open questions remained about the exact chemical mechanisms involved.
And finally, coating the cathode particles.
Just like coating anodes, yes. They discussed coating cathode materials, like NMC, with thin layers of things like zirconium oxide, ZrO2. Again, the goal is to stabilize that interface between the active material and the electrolyte.
Protecting it from side reactions.
Exactly. Improves cycle life, stability at high temperatures. It highlights that optimizing performance requires looking at interfaces on both the anode and the cathode side.
Okay, we have definitely gone deep today, really unpacking this research collection almost chapter by chapter like we planned.
It really gives you a sense of the breadth and depth of work just on carbon materials for energy storage. It's everywhere, doing different jobs.
From supercaps needing that massive surface area
To metal air needing robust, gas-permeable, water-managing electrodes.
and especially lithium-ion anodes, with all the complexity of the SEI, the intercalation, the volume changes.
Carbon is the common thread, but the challenges and solutions are incredibly diverse depending on the application. We saw so many strategies tweaking pores, additives, coatings, composites, synthesis methods.
And it really drives home how this fundamental science, the kind presented in these workshop proceedings, directly feeds into making better batteries and energy storage for all of us.
Absolutely. Longer-lasting electronics, more capable EVs.
It starts here.
So thinking about all these different carbon forms we've discussed, graphite, hard carbon, TEG, nanotubes, aerogels, and all the ways they're being modified and combined.
It just makes you wonder, right? With all this focus on optimizing what we know, what completely different, maybe even counterintuitive carbon structures or carbon-based composites might still be out there undiscovered? Could there be some form of carbon we haven't even synthesized yet that leapfrogs all of these materials and unlocks a whole new level of energy storage?
That's a fascinating thought. What's the next truly disruptive carbon material?
Something for you, the listener, to maybe ponder next time you plug something in.